Hi guys, welcome to a problem set from chapter 14, Solutions. This chapter incorporates a lot of topics from earlier chapters in the book, including the ideal gas law, partial pressure, mole fraction from chapter 6, and intermolecular forces, which you may remember fairly recently from chapter 12. But there are other ones as well, but we'll encounter them as we go along. So I'm going to be going through several examples, and my recommendation for you is that as you're listening to me talk and kind of describe the problem, try pausing it and figuring it out on your own. And if you get stuck, then you can move on to the solution slides. No pun intended there. So I think that that's just a more effective way to learn the problems, but whatever works for you. Vitamins are often categorized as either fat soluble or water soluble. Water soluble vitamins, because there's a lot of water in body fluids, they dissolve easily in body fluids and can be eliminated through the urine. So over-consuming them is unlikely. However, with fat-soluble vitamins, fat accumulates in the body. So vitamins that dissolve in fat are going to likely remain in the body, and overconsumption can be dangerous to your health. So if we're looking at, for example, vitamin C, we first have to look at the bonds present in the molecule itself to determine if there's likely to be a net dipole for this molecule. Because like dissolves like, polar substances are attracted to polar substances. Non-polar substances are attracted to non-polar substances. So this question is basically saying, like, okay, are these molecules polar? And if they are, they're more likely to be water soluble. The ones that are mostly non-polar will be fat soluble. So for vitamin C, look at the bonds in vitamin C. We've got carbon-oxygen bonds, we've got oxygen-hydrogen bonds. So remember from chapter 12, oxygen-hydrogen bonds, those molecules that have those can engage in hydrogen bonding with other molecules that have similar bonds. Okay, so we've got all of these here. So because of that, it's likely that this molecule has a net dipole, and it's a polar substance. For B, we do have these polar bonds within the molecule, but we also have to consider the location of these bonds. Notice how they are pretty much equal and opposite each other. And remember that when you're considering if a molecule has a net dipole, you're thinking in terms of vector quantities, right? Remember this arrow here that symbolizes a dipole. The more negative or the more electronegative atom is on this side of the bond. The less electronegative atom is on that side. So if we're talking about a dipole, okay, those bonds are identical, right? And they're equal and opposite each other. It's likely that they're just going to cancel each other out. And while carbon and hydrogen, there is a slight difference in electronegativity between carbon and hydrogen, that's still not enough for it to be considered a polar molecule. Okay, so when you've got these dipoles canceling each other out, likely you have a non-polar molecule. For vitamin A, we've got a really long hydrocarbon chain here. We do have an OH group there. But overall, we've got a very large structure that only consists of carbons and hydrogens. So that OH group on the end, while it may make it slightly more likely for this molecule to be water soluble, you have to consider the size of the structure itself. Because the overall structure massively consists of carbons and hydrogens, this is likely a non-polar molecule. And then for part D, Again, examine the bonds. There's quite a few carbon-oxygen, oxygen-hydrogen. There's a nitrogen-hydrogen bond in here. So if we're looking at these bonds, we've got quite a few polar bonds in this molecule. So chances are this is a polar molecule. Okay, so for part A, if we're looking at vitamin C, you've got these 4 OH bonds, making it really polar and likely to hydrogen bond with water. Therefore, vitamin C is water soluble. For part B, okay, the carbon-carbon bonds in vitamin K3 are nonpolar. The carbon-hydrogen bonds, they do have a difference in electronegativity, but not significant. And the carbon-oxygen bonds are polar. However, like I said, they're opposite each other and most likely cancel each other out. So therefore, this molecule does not have a large net dipole and is not considered a polar molecule. Therefore, because it's nonpolar, it's soluble in another nonpolar substance, which in this case would be fat. So vitamin K3 is fat soluble. For vitamin A, where we have a lot of carbon and hydrogen bonds, and then in this case, we do have an oxygen and a hydrogen, but it's only a small part of this huge molecule. The molecule is really dominated by the carbon-hydrogen bonds. Most of the molecule is likely to engage in bonding with fat because most of the bonds are relatively nonpolar. For part D, we've got quite a few polar bonds. So therefore, vitamin B5 is more likely to dissolve in water because water is also polar. Determine whether each compound is soluble in hexane. Okay, well, first we need to consider what hexane is. Recall that, I believe this is in chapter 3, how you can determine the structure of a hydrocarbon based on the name and vice versa. So hexane, that prefix is implying that there's 6 carbons, and that suffix or the end of that word, ane, implies that this is an alkane, so it only has single bonds. So you would have 6 carbons, and 14 hydrogens. As you can see, this is a completely non-polar molecule. It's symmetrical and it only has carbon-hydrogen bonds and carbon-carbon bonds. Okay. So this is a non-polar substance. Remember that like dissolves like, right? So in order for a compound to be soluble in hexane, it would need to be a non-polar substance. If we think about the water, as I said in the last problem, I think we're all pretty comfortable with the idea that water is a polar substance. So chances are these are not going to mix together. Propane, well, propane also only has carbon-carbon bonds and carbon-hydrogen bonds. Propane is nonpolar. Ammonia, maybe I should just draw the structure for ammonia. Well, first I'll draw the structure for water, which everybody knows. Okay, and then ammonia. Okay, so both of these have a permanent dipole. Both of them engage in hydrogen bonding. Okay, so both of them are polar molecules. Ammonia is polar. Hydrogen chloride. Okay, this is also a polar molecule, right? Because there's a difference in electronegativity between the two atoms. Okay, so if we look at our contenders, we have 3 polar substances and 1 nonpolar substance. So which ones are likely to be miscible with hexane or soluble in hexane? Propane is the only one that's going to be soluble in hexane because it has similar intermolecular forces and it's nonpolar. Okay. Like dissolves like. Just say that to yourselves over and over again like a mantra. So switching gears here, the next problem deals with Henry's law, which is a law that quantifies the solubility of a gas when there's a change in pressure. And Henry's law is associated with a formula. Okay? It can be articulated as follows. So the solubility of a gas equals, this is called the proportionality constant, times the pressure of the gas. Okay, so solubility is a unit in molarity. Okay, so moles over liters. The proportionality constant is molarity over atmospheres, and then the pressure of the gas is in atmospheres. Okay, so the proportionality constant, or the Henry's law constant rather, depends on the specific solute and solvent that you're talking about, and also the temperature. So it's a literature value. If this were an exam, you would probably have to be given this value. This is not something that you would be memorizing or just know off the top of your head. Okay, but you would need to know how to implement it. So in the book, table 14.4, that has several Henry's law constants for different gases, and they're all at 25 degrees Celsius, which is what this is here. The one for carbon dioxide, the Henry's law constant for carbon dioxide is 3.4 times 10 to the negative second molar per ATM. Okay, so we'll keep that in mind. Okay, now the solubility of the carbon dioxide in the bottle of club soda is 0.12 molar. So we're going to say the solubility is 0.12 molar. And we're being asked to find the pressure. Now, before I just kind of go in and use the formula, this is a fairly simple calculation. This is useful in terms of understanding why when you open a can of soda, there's like that fizzing sound and then a bunch of bubbles come up through the liquid that's in the can. Okay, so when the pressure changes inside the can, in other words, when the can is open, the carbon dioxide that was dissolved in the soda is going to evaporate from the soda into the space above the liquid because there was a decrease in pressure and it's trying to go back to equilibrium. Okay. So if we're looking at this and we need to find the pressure of the CO2, we simply have to rearrange this formula and solve for pressure. Okay, so the pressure of the CO2 is just the solubility of the CO2 over the Henry's law constant. .12 molar by 3.4 times 10 to the negative second. And you get 3.5 atmospheres. Okay, so that's 3.5. For part B, determine the solubility of oxygen in water at 25 degrees Celsius exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. Okay, so we're only interested in the oxygen here, right? So we see that the partial pressure of the oxygen is 0.21 atmospheres. I'm just going to draw a line here to demarcate these two problems. This is problem A, problem B. Okay, so the solubility of the oxygen is going to equal the Henry's law constant of the oxygen times the partial pressure of the oxygen. And according to that table, table 14.4, I'll just write it up here, table 14.4, the Henry's law constant for oxygen is 1.3 times 10 to the negative third molar per ATM. Okay, the pressure is 0.21 ATM, and we need to find the solubility. So we're just going to plug those values in. Okay, 2.7 times 10 to the negative fourth molar. Okay, because remember, solubility is in moles per liter. Okay, so I'll just write that up here. Okay, so hopefully that makes sense. Henry's law, it's a very simple calculation. You just need to understand what these variables are. Okay, using parts by mass and calculation. So this is not really new. We've got some concepts here that harken back to chapter 4. When we're just trying to figure out parts by mass, we're looking at percents. So this is not new territory, but it's good to have a refresher, okay, because this is going to be incorporated into problems further on. So, okay, what volume in milliliters of a soft drink that is 10.5% sucrose by mass contains 78.5 grams of sucrose? Okay, so notice that we've been given the percentage of sucrose, the mass of the sucrose, and then the density of the whole solution. Okay, so remember, I mean, I'm sure I don't have to tell you this, but density, right, is mass over volume. And density can be used as a conversion factor, right? So if you're starting out with, for example, grams, and you want to get to milliliters, the density is going to be how you get there. Okay, likewise, same thing. Okay. So first of all, let's think in terms of, okay, what's going on here? We, first of all, could probably figure out the mass of sucrose in this compound. Or sorry, we could probably figure out the mass of the overall soft drink. Okay, I'm going to pause for a second. Okay, so we can probably find the mass of the soft drink if we know that 10.5% of it is sucrose, and then that 10.5% weighs 78.5 grams. Like, how much does the whole thing weigh, right? So let's start with the 78.5 grams of sucrose. Okay, like the fact that we know that we have 10.5% sucrose, that means that we have 10.5 grams of sucrose per 100 grams of solution, right? That's like the concept of a percent, right? 10.5% of 100 is 10.5. So why don't we use that percentage as a conversion factor too, okay? So if we're starting with this 78.5 grams of sucrose, And we know that for every 100 grams of solution, we have 10.5 grams of sucrose. And we know that because the density is 1.04 grams per milliliter, that 1.04 grams of solution is present in 1 milliliter of that solution. We can cancel out grams of sucrose, grams of solution, and we're left with just milliliters of solution. So then that would end up being 719 milliliters of solution or of soft drink, right? Because a soft drink is a solution. A soft drink is a homogeneous solution. Okay. Not too bad, right? Okay, so this is from a slightly different perspective. What massive sucrose in grams is contained in 355 milliliters of a soft drink, or 12 ounces of a soft drink, that is 11.5% sucrose by mass. And then we're given the density of the soft drink, or of the solution rather, okay? So we're gonna follow the same principle that we did for the other problem. So we've got a volume of 355 milliliters. You know what? I think I'm just going to go back. Let's redo stuff. So here we're revisiting some concepts that were covered way back in chapter 4 when we're considering composition by mass, like we're dealing with percents. This is actually, there's nothing really new here. This is just sort of a refresher on how you can use density as the conversion factor between mass and volume, or volume and mass. Okay, so what volume in milliliters of a soft drink that is 10% sucrose by mass contains 78.5 grams of sucrose? And then we're given the density of the solution. Okay, so the solution is the soft drink, right? A soft drink is a homogeneous solution. So the density of the soft drink is 1.04 grams per milliliter. Okay, so we'll just write that down. Density of the solution, 1.04 grams per milliliter. The mass of the sucrose is 78.5 grams. The percent of the overall compound, or sorry, the percent of the soft drink by mass, that's sucrose, is 10.5%. So what that's basically saying is that there's 10.5 grams of sucrose and 100 grams of solution. Okay, so 100 grams of this soft drink contains 10.5 grams of sucrose. That's basically a percent, right? 10.5% of 100 is 10.5. So let's use this as a conversion factor, shall we? Okay, so we're starting with the mass of a component of the soft drink, and we need to get to the volume of the entire soft drink. So basically, we need to get from the mass of the sucrose to the mass of the soft drink to the volume of the soft drink. And we can do that by using density. Density is also a conversion factor, right? Okay, so if we're starting with 78.5 grams of sucrose, we know that there's 10.5 grams of sucrose and 100 grams of solution. So I'm doing dimensional analysis here based on, okay, I started with grams of sucrose, so whatever my next fraction is should have grams of sucrose in the denominator. This is my variable that's dealing with grams of sucrose in a conversion factor. Okay, so 100 grams of solution per 10.5 grams of sucrose. Okay, so now we have to convert those grams of solution to milliliters of solution. And here we go. We have density here to help us do that. So there's 1.04 grams of solution in 1 milliliter of solution. And that results in 719 milliliters of solution, okay, or soft drink. Okay. Not bad, right? So this one is doing the opposite. Now we're given the volume of the entire soft drink, the percentage of the sucrose by mass, and we're being asked to find the mass of the sucrose. Okay, so what mass of sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. Okay, so let's just write out what we know. The volume of the solution is 355 milliliters. The percentage of the sucrose in terms of mass, okay, 11.5 grams of sucrose and 100 grams of solution. There you go. Okay, that's a conversion factor. The density of the solution is 1.04 grams per milliliter, also a conversion factor. Okay, so we're starting with this. We need to get from milliliters of the solution to grams of the solution to grams of the sucrose. Okay, that's our plan. So we're going to start with 355 milliliters. Okay. To get to this part, grams of solution, we know that there's 1.04 grams of solution in 1 milliliter of solution. We know that in 100 grams of the solution, we have 11.5 grams of sucrose. And I believe that's all the information that we need. Okay, so milliliters of solution cancels out, grams of solution cancels out. We're just left with grams of sucrose. So the result should be 42.5 grams of sucrose. Okay. Okay, a water sample is found to contain the pollutant chlorobenzene with a concentration of 15 ppb by mass. What volume of this water contains 5 times 10 to the second milligrams of chlorobenzene? Assume a density of 1 gram per milliliter. Okay, so first of all, let's just address what ppb means. So further on in the major, when you are taking, for example, instrumental analysis, you're going to encounter this terminology a lot more often, like ppb or ppm. And ppb means parts per billion, just like ppm would mean parts per million. So 15 ppb means that there's 15 parts of chlorobenzene per 1 billion parts water. And this is by mass. So I might just write this in grams. So 15 ppb is like saying 15 milligrams of chlorobenzene per 1 billion milligrams of water. Okay, so, or it could be like 15 grams of chlorobenzene per 1 billion grams of water. Means the same either way, you know, as long as your units are consistent for the solute and the solvent. Okay. So now that we know that, we see that this is really a conversion factor, right? So we're going to approach this problem just like the last two. We're starting with a mass and we're being asked to find volume. So somewhere in there, we're going to have to use density as a conversion factor between mass and volume. But first, let's start with what we were given. Okay, so we have 5 times 10 to the second milligrams of chlorobenzene. Now we know that there's 15 milligrams of chlorobenzene in 1 billion milligrams of water. The density of water is 1 gram per milliliter. Okay, so we could say that, let's just quickly convert that to milligram or to, let's convert milligrams. Okay, so there's 10 to the third milligrams in 1 gram. Okay, the density of water is 1 gram, or I should say 1.00 grams per milliliter. And I'm just going to, I'm going to convert this to liters because this is going to be a huge number. Okay, so there's 1,000 milliliters in 1 liter. Okay, so we're going to be left with liters of H2O at the end. Okay, so that's going to end up being okay, 3.3 times 10 to the 4th liters of water. Okay, so just to recap, we started with the mass of chlorobenzene. Just like in the previous examples where we were given percent by mass, this is a similar concept where we're saying parts per billion by mass. Okay, so that's what this part is here. And to get to the end, I mean, you could have found this answer in milliliters and put it in scientific notation and that would have been fine. I just, as a matter of personal preference, put it in liters. Okay. Okay. A solution is prepared by dissolving 17.2 grams of ethylene glycol in 0.5 kilograms of water. The final volume of the solution is 515 milliliters. Calculate the concentration of the solution in each unit. So we have to find the concentration in molarity, which is moles per liter. Molality. Molality is new. Molality is not molarity. They look different by only 1 letter, but they are actually very different things. Okay, so molality, and actually to go back and be more specific about molarity, right? Molarity is moles of solute per liters of solution. Molality is moles of solute per kilogram of solvent. This is different, right? Solvent and solution are not the same thing. So molarity is dealing with the volume of the solution, while molality is dealing with the mass of the solvent. The solvent, again, is what does the dissolving, right? And then we have to find percent by mass, the mole fraction, and the mole percent. And mole percent might seem alien to you, but honestly, like that's just the mole fraction times 100. So there you go. Not too bad. Okay, so we'll do the first 2 parts. Okay, so we've got 17.2 grams of ethylene glycol and 0.5 kilograms of water. Notice that we've been given the formula for ethylene glycol, which is significant here, right? Because if you're given the mass, and you need moles, you can calculate the moles using the molar mass of the compound, right? So first, let's just figure out how many moles of ethylene glycol we have. Okay. Okay. We have 17.2 grams of it. And based on the periodic table and adding up the individual molar masses of all the elements in the formula, 1 mole of ethylene glycol is about 62 grams. Okay, so now we're left with 0.2771 moles of ethylene glycol. Now, 0.5 kilograms of water. Okay, the final volume of the solution is 515 milliliters. Okay, so remember, molarity is moles of solute, the thing that's being dissolved, right, over liters of solution. The volume in liters. Okay, so 515 milliliters is 0.515 liters, right? Divide by 1,000. So the moles of ethylene glycol, 0.2771. Our solution, 515 milliliters, which is 0.515 liters. Okay, so divided by 0.515 liters. Okay, 0.538 molar. That's it. Okay, find the moles, divide it by the volume of the solution. Part A. Okay, part B, for molality. Molality is represented by a little m. Okay, so molarity, this is a very important distinction. Molarity is capital M, molality is lowercase m. That is moles of solute over kilograms of solvent. So we've been given the kilograms of the solvent in the problem. It's 0.5 kilograms. And we calculated the moles from the last step. So we just need to divide the moles of ethylene glycol okay, 0.554. And I should be a little bit more clear with my writing there. Molal, I believe is how that's said, lowercase m. Okay, not too bad, right? I'm going to say not too bad about 500 times during this. Okay, next part, we have to find the percent by mass of this. So I think, you know, you guys should be experts in percent by mass at this point. But percent by mass is going to be the percent of ethylene glycol over the percent mass, or sorry, the percent of ethylene glycol in the solution. So maybe this is actually a little bit trickier because remember, the mass of the solution is not necessarily going to be the mass of the water, right? Because the mass of the solution includes the water and the ethylene glycol. So let's just make sure that we're consistent here. Okay, so like the mass of the ethylene glycol is 17.2 grams. The mass of the water is 0.500 kilograms, which is 500 grams. Let's just be consistent. Okay, so percent by mass, you're dividing the mass of the ethylene glycol by the mass of the whole solution. So you have to add those two masses together. Okay, and because it's a percent, you have to multiply it by 100, which ends up being 3.33%. Mole fraction, that's going to be the moles of the ethylene glycol divided by the total moles, meaning the moles of ethylene glycol plus the moles of water. So we already have the moles of ethylene glycol from the previous part of the problem. Okay. For moles of water, we've got 500 grams of water, 1 mole of water, 18.016 grams. So we have 27.75, underlining my least significant digit, moles of water. Okay. Okay, so I am taking this value, I'm going to insert it here. So we're dividing 0.2771 moles of ethylene glycol by the sum of the moles of the ethylene glycol and the water. And for this, I got 9.89 times 10 to the negative third. And remember, mole fraction is unitless, right? Because you're just dividing moles by moles. So those units will cancel each other out and it's just unitless. Mole percent. You're just taking that 9.89 times 10 to the negative third and multiplying it by 100 to get a percent. So that's 0.989%. Okay. So your percent by mass is 3.33%. Your mole fraction is 9.89 times 10 to the negative third. And your mole percent is 0.989%. Very similar example. A solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. So again, same thing, same stuff. Okay, so we've got the mass of the solute, we've got the mass of the solvent, and we've got the volume of the solution. So let's start with molarity again. Okay, so in order to do either molarity or molality, we need to know how many moles of solute we have, which in this case is sucrose. So let's convert the mass of sucrose to moles. Okay, 1 mole of sucrose, molar mass of sucrose is 342.296 grams. I suppose I should write the formula out. Okay, so that ends up being 0.147, the 7 being the least significant digit, 2 moles. Okay, so for molarity, we need moles of solute over liters of solution. Okay, so our liters of solution, well, it's 355 milliliters, right? So that's 0.355 liters. Okay, so 0.1472 moles of sucrose divided by 0.355 liters of solution. And that ends up being 0.415 molar. For part B, molality, again, moles of solute over kilograms of solvent. Okay, so again, 0.1472 moles of sucrose. And we've got 0.332 kilograms of water. Little m. My little m and my big M don't look very different from each other, but please keep in mind that is a little m. And, you know, I should also say, those of you who have had me in the past know that, you know, I complain about this all the time where I have less control over my handwriting with this tablet. So if, you know, I apologize if you have difficulty reading my handwriting sometimes. I'm doing my best to be consistent with it, but hopefully my descriptions are helping in case you're looking at it going, what? Okay, percent by mass. 50 grams of sucrose, 0.332 kilograms of water, or in other words, that's 332 grams of water. So remember, percent by mass, the mass of the whole thing, it's the mass of the solution. In our previous examples, we were given the density of the solution and the volume of the solution, and that's how we found the mass. But here we're not given density, but we are given the masses of the two components, right? So percent by mass, we're just going to divide the 50.4 grams of sucrose by the sum of the masses of both of those components. And then we have to multiply that by 100, right? So then that would give us 13.2%. The mole fraction. Okay, so we have the moles, that would be the moles of sucrose but divided by the total moles. So again, we need to find the moles of water here. Okay, so that's about 18.428 moles of water. Okay, so our mole fraction for sucrose is, and mole fraction is symbolized by an X, right? Is 0.1472 moles of sucrose divided by the sum of the moles of sucrose and water. Okay, so that's your mole fraction. It's unitless, right? And then percent, mole percent is just going to be that number times 100. Okay. So our percent by mass is 13.2. Our mole fraction is 0.00792, and our mole percent is 0.792%. What is the molarity of a 6.56% by mass glucose solution? Okay, so here we're given the glucose. Sorry, here, yeah, we are given the glucose, but we're also given the density of the solution. We're not given the mass of the solution itself, but that's okay. All right, so 6.56% by mass glucose means that there's 6.56 grams of sucrose in 100 grams of solution. Okay, conversion factor there. And we're being asked to find molarity. So remember, molarity is the moles of solute divided by the liters of solution. So we have to somehow use this information given to find the volume of the whole solution. Okay. So if we're given the density as well, okay, what is the molarity of a 6.56% by mass glucose solution? The density of the solution is 1.03 grams per milliliter. Okay, so it seems that we're given some sparse info, but it's enough to solve this problem. So we're trying to find the concentration of something where we only know two things: what the percentage of it is by mass, and then what the density of the solution is. So since it's 6.56% by mass, why don't we just say that we have 6.56 grams of glucose and we have 100 grams of solution. Okay. So in order to find molarity, remember molarity is moles over liters, moles of solute over liters of solution. We can easily find the moles of our solute because we have the mass of our solute, right? So 6.56 grams of glucose. Okay, molar mass of glucose is 180.156 grams. Okay, so that'll give us our moles. If we have 100 grams of solution, and we know that the density is 1.03 grams per milliliter, then we know that there's 1.03 grams of solution in 1 milliliter of solution. And then because molarity uses liters as a unit, we're going to convert that to liters. Okay, so now our molarity is our moles of solute over liters of solution. So 0.03641 moles of glucose divided by 0.097087 liters of solution. And that should be 0.375 molar. Okay. This is the same exact problem, except with a different percentage. Okay, so, you know, this goes for all of these problems. Like, feel free to pause and try to do this on your own before watching the answer being written out. Okay, so again, let's just say we have 10.5 grams of glucose. Okay, maybe I'll read the question. What is the molarity of a 10.5% by mass glucose solution? And the density of the solution is 1.03 grams per milliliter. Okay, so we'll say that we have 10.5 grams of glucose, and we'll say we have 100 grams of solution. So first, let's find how many moles of glucose we're dealing with. Okay. Okay, so halfway there, now we need, in order to find molarity, we need the liters of solution. So if we've got 100 grams of solution, and we know that 1 milliliter of the solution weighs 1.03 grams. Oh, and we need it in liters, right? Okay, so molarity, moles of solute over liters of solution. And that is 0.6 molar. Okay. Now, don't be deceived here. This is not a mistake. This is not the exact same question as the previous one, because look, molality. What is the molality of a 10.5% by mass glucose solution? So we need to go back and determine what the mass of the solvent is in this case, because remember, molality is moles of solute over kilograms of solvent. Got to watch out for that L. Okay, so moles of solute, this is the same as the previous problem. I'll write it out anyway. Okay, so let's say that if it's 10%, 10.5% by mass glucose, that means that we've got 10.5 grams of glucose per 100 grams of solution. Okay, so let's consider this for a second. If the whole solution weighs 100 grams and the solute weighs 10.5 grams, how much does the solvent weigh? Well, the mass of the solution is, of course, the mass of the components added up together. Okay, so the mass of the solvent is just subtracting the mass of the solute from the overall mass of the solution. Okay, so that is just going to be 100 grams minus 10.5 grams. So that is 89.5 grams of water. Okay, we're assuming that this is an aqueous glucose solution. I mean, you could just say, you know, you could just say solvent if you wanted to. Okay, so, all right, that is going in kilograms, that would be 0.0895 kilograms. Okay, so we've got one piece of information there. After that, we have to, again, go back and find the moles of the glucose, which we did in the previous problem, but I'm just going to redo it. Okay, so the molality is going to be the moles of solute over kilograms of solvent. So okay, 0.651 molal. So be careful. This is a common mistake that I see, and a mistake that I even make occasionally, where you forget to consider that solution and solvent are not going to have the same mass, right? Because the solution also includes the solute. Okay, switching gears again. Okay, calculating the vapor pressure of a solution containing a non-electrolyte and a non-volatile solute. So a non-electrolyte does not break up into ions, and you're talking about most molecular compounds with the exceptions of acids. So in this case, sucrose is a non-electrolyte. And this question, okay, let's first read it. Calculate the vapor pressure at 25 degrees Celsius of a solution containing 99.5 grams of sucrose and 300 milliliters of water. And then you're given the vapor pressure of pure water at 25 degrees Celsius, which is 23.8 torr, and then the density of water. So just to go over a little bit of what is in the chapter, like what the point of this is, vapor pressure of a solution is less than the vapor pressure of a pure solvent. Okay, so the vapor pressure, whatever answer we get for this problem, is going to be less than 23.8 torr. And the reason it's less can be explained mainly in two ways. One, there's a tendency towards mixing. Okay, so if you put a solute into a solvent and it's dissolving, those solute particles are interfering with the solvent particles' ability to evaporate. That's one thing. Another is the rate of vaporization is affected. Okay, the dynamic equilibrium is affected when the solute is added. So in order to regain that equilibrium, more gas may need to condense back into liquid, which is going to lower the vapor pressure. Okay, it's all in the book. So this information, the way in which, or like the amount by which the vapor pressure is lowered, can be quantified by Raoult's law, and I may be mispronouncing that. So Raoult's law says that the pressure of a solution, or the vapor pressure of a solution, is going to be the mole fraction of the solvent times the vapor pressure of the pure solvent at the same temperature. Okay, so, you know, all right, I'll make this a little bit more concise. Okay, so it's again, kind of like Henry's law, it's a 3-variable equation. So if you have 2 parts, you can find the third part. So everything is occurring at the same temperature here. So this little circle that usually represents like standard conditions. In this case, it's referring to like all of these things are occurring at the same temperature. So if we're calculating the vapor pressure of a solution where you have 99.5 grams of sucrose, and we were given the water, and we're given the vapor pressure of water. Okay, so we've been given this. We know that. We don't know what this is, and we also don't know what this is. But the information that we've been given can help us figure out what the mole fraction of the solvent is. Okay, so first of all, the solvent is water, right? The pressure of the pure solvent is 23.8 torr. The volume of the solvent is 300 milliliters. Extra zero there. 300 milliliters of water. And the density of water is 1 gram per milliliter. Okay, so we're going to have to somehow use this information to get to mole fraction. Remember that the mole fraction of water, because we need to find the mole fraction of the solvent, right? So the mole fraction of water is going to be the moles of water divided by the moles of water plus the moles of the sucrose. So we need to find moles of water and moles of sucrose. So maybe we could start with the easiest part, which is finding the moles of sucrose. Okay. Maybe I'll use a different color pen here. Okay. So here we've got 99.5 grams of sucrose. Let's convert that to moles. Okay, 0.2906 moles of sucrose. To find the moles of water, well, since the density of water is 1 gram per milliliter, I'm going to say the mass of the water is 300 grams, right? Because if we have a 300 milliliter solution and the density is 1 gram per milliliter, therefore the mass is 300 grams. Okay, so 300 grams of water . 16.65 moles of water. Okay, so the mole fraction of water is going to be that 16.65 divided by the sum of the moles of the sucrose and the water added together. I actually didn't do this out. Okay, it's around 0.98284. Oops, and that's unitless. Pardon me. Okay, now finally, to find the pressure of the solution, we're going to plug this equation into, or we're going to plug this information into the Raoult's law equation. Okay, so that will be this last part here in blue. Okay, so the pressure of the solution is going to be the mole fraction of the solvent times the pressure of the solvent. Okay, so that's going to be 0.98284 times 23.8 torr. And we will end up with 23.4 torr. So let's just think about this. Is this consistent with what I said earlier, that the vapor pressure of a solution is lower than the pure solvent? And yes, it is. Okay. Calculate the vapor pressure at 25 degrees Celsius of a solution containing 55.3 grams of ethylene glycol and 285.2 grams of water. All right. So we're dealing with, kind of a similar situation as the last problem. So we're going to follow the same steps here. Let's first write out like everything that we know. Okay, so this is a Raoult's law question because we're finding the vapor pressure of a solution, right? So the pressure of the solution is going to be the mole fraction of the solvent. So in this case, the solvent's water. So the mole fraction of water times the pressure of water, pure water at the same temperature. Ethylene glycol, okay, we got 55.3 grams of ethylene glycol. Now, let's think about okay, so the formula has been presented to us like this. We know that we're going to need to find the moles of this at some point. So I think it's often a good idea to, when you're determining the molar mass and the formula isn't written out in the conventional way, to just make sure you count everything up accurately. So, okay, we've got 1, 2, 3, 4, 5, 6 hydrogens. We have 2 carbons, and we have 2 oxygens. Okay, so the molar mass of this is going to be okay, 62.068 grams per mole. Okay. The vapor pressure of water is 23.8 torr. Okay, so the pressure of the water, 23.8 torr. And the mass of the water is 285.2 grams. Okay, so first, so we've been given the pressure of the water and we need to find the mole fraction. So we need to find the moles of the ethylene glycol. So if we've got 55.3 grams of ethylene glycol, just going to abbreviate it EG. Okay, and then 1 mole of that is 62.068 grams. That means that we have 0.89095 moles of ethylene glycol. If we have 285.2 grams of water, 1 mole of water, 18.016 grams. Okay, so now we got 15.83 moles of water. The mole fraction of water is going to be the moles of water divided by the total moles. So we've got the 15.83 moles of water. Hopefully you can see the bottom of the screen. Okay, so at the bottom there, you can see the moles of water plus the moles of ethylene glycol. Okay, so that's about 0.9467. Okay, so that's the mole fraction of water there. Now the last step is to find the pressure of the solution. And that's going to be the mole fraction times the pure solvent. (22.5 torr). Okay, so there you go. It makes sense because the value is lower than the pressure of the pure solvent. Okay. A solution containing ethylene glycol and water has a vapor pressure of 7.88 torr at 10 degrees Celsius. Pure water has a vapor pressure of 9.21 torr at 10 degrees Celsius. What's the mole fraction of ethylene glycol in the solution? Okay, well, let's ruminate on this for a second. I think that this is actually pretty straightforward because we're only being asked to find the mole fraction of the ethylene glycol. In order to do that, okay, let's just remind ourselves of the formula, right? And I highly recommend writing this formula out with the little subscripts as to what all of the variables represent. Because remember, we're dealing with a solute and a solvent. And Raoult's law is mainly pertaining to like the solution relative to the solvent, not the solute. Here we're being asked to find the mole fraction of ethylene glycol. Ethylene glycol is the solute, okay? Let's remember, the pressure of the solution equals the mole fraction of the solvent times the pressure of the solvent at the same temperature. Okay, so we can easily solve for the mole fraction of the solvent, but then we need the mole fraction of the solute, right? I guess I'm writing in blue now. Okay, so P solution is 7.88 torr. Okay, it's at 10 degrees Celsius. The other pressure is also at 10 degrees Celsius. Okay, the pressure of pure water vapor is 9.21 torr. So the mole fraction of the solvent, which is water, is going to be the pressure of the solution divided by the pressure of the solvent or of water. Okay, underlining least significant digit. Okay, so the mole fraction of water is 0.8555. Are we done? No, we're not. There's one last step because we're being asked to find the mole fraction of ethylene glycol. Okay, so remember, just like all percentages add up to 100, all fractions have to add up to 1. So in order to find the mole fraction of the solute, we're just going to subtract the mole fraction of the solvent from 1. And there you go. So that would be the mole fraction of ethylene glycol in this solution. So here we come to a question involving a two-component solution. So the previous questions were specifically dealing with non-volatile solutes, meaning that the substance that was dissolved in the solvent was not going to vaporize. Okay, only the solvent was vaporizing. In this case, you've got two components which are both volatile. So they're both evaporating or vaporizing. And so both of them are going to exert their own partial pressure over the solution. In a case like this, you treat each individual gas like you would in the previous questions with Raoult's law, except now you're doing it in terms of partial pressures. Okay, so let's say that we have gas A and gas B, right? And we have like a mixture of these two. So the pressure exerted by gas A is going to be the mole fraction of that gas times the pressure of the gas over its pure liquid. Okay. The same for B. Okay, this is just like the previous example, except, now we're specifying which one is which. And the total pressure is going to be the sum of those partial pressures, which is consistent with Dalton's law of partial pressures. Okay, so for this first example, a solution contains 3.95 grams of carbon disulfide and 2.43 grams of acetone. At 35 degrees Celsius, the vapor pressures of pure carbon disulfide and pure acetone are 515 torr and 332 torr. Assuming ideal behavior, calculate the vapor pressures of each component and the total vapor pressure of the solution. So, okay, let's write down what we've been given in the problem. 3.95 grams of carbon disulfide, 2.43 grams of acetone. Okay, so the formula for acetone is C3H6O. And the pressure of pure carbon disulfide is 515 torr. The pressure of pure acetone is 332 torr. Okay, so what can we do with this information? Remember, going back to the formulas, right? Just to find the partial pressures, we're going to be multiplying the mole fraction of one particular gas by the pressure of the gas over its pure liquid. Okay. So a good place to start here is probably converting each of these to moles, since we need to find the mole fraction, right? So for the carbon disulfide, okay, acetone Okay. Let's find, so going back to the example where we had to find the mole fraction of the solute, we only need to find the mole fraction of one of these, and then we can find the other one by subtracting it from one. Okay, so let's just find the mole fraction of the acetone, for example. So the mole fraction of the acetone is going to be the moles of acetone over the moles of acetone plus the moles of the carbon disulfide. Okay, so that's our mole fraction for acetone. And remember, mole fraction is unitless, right? So therefore, the mole fraction of the carbon disulfide is just 1 minus the mole fraction of the acetone. Because remember, just like all percentages add up to 100, all fractions add up to 1. And I should be underlining my sig figs here, pardon me. Okay. So now we have our mole fractions. And the last thing to do is add, or I'm sorry, the last thing to do is calculate the partial pressures for each of these using the pressures of the pure substances times their mole fraction. So for the pressure of, I'll write this in a different color. The pressure of the carbon disulfide is going to equal the mole fraction actually, you know what? I should probably write the formula. Okay, so that's the mole fraction of carbon disulfide times the pressure of pure carbon disulfide. Okay, so that's going to be 0.554 times this value, 515 torr, which is going to equal 285 torr. Okay, likewise, the pressure of the acetone is going to be the mole fraction of the acetone times the pressure of pure acetone. Oops. Putting the cart before the horse here, which is 332 torr. So that is 148 torr. Okay, so now we have our partial pressures for each gas. Now we need to find the total pressure. Okay. I need some room, but I think what I'm going to do is I'll just write it up here. Okay, so the total pressure is just the sum of the partial pressures. And that is 433 torr. So that is the total pressure above the solution. Okay, that's part A done. Hopefully this is making sense. Okay, the experimentally measured total vapor pressure of the solution at 35 degrees Celsius is 645 torr. Is the solution ideal? Okay, remember, an ideal solution follows Raoult's law pretty closely. So the actual value would be pretty close to the predicted value. What we got in our calculations was 433 torr. For this carbon disulfide and acetone mixture. So that is significantly less than 645 torr, which is the actual vapor pressure of the solution. So what's going on here? Why is the actual vapor pressure of the solution much higher than predicted? And we have to think of this in terms of intermolecular forces, okay? If the solute and solvent interactions in the solution are weaker than the solvent-solvent interactions, that means that more particles in that solution are likely to vaporize and become a gas. So, I mean, if you think about it, if the particles are not interfering with each other's ability to evaporate, they're going to evaporate more easily or vaporize more easily. On the other hand, if you have stronger solute-solvent interactions than solvent-solvent interactions, that solution is going to be less likely to vaporize. Okay, so those are the situations in which you deviate from Raoult's law. It's either going to be greater than expected or less than expected. So this is discussed in the textbook. There's a diagram in figure 14.15. That illustrates the pattern in how certain solutions deviate from Raoult's law. So that kind of answers our question for part C. Okay, so first of all, for part B, this is not an ideal solution because the predicted value is much lower than the actual value. And it's saying, what can you say about the relative strength of the carbon disulfide to acetone interactions compared to acetone and carbon disulfide interactions? So this is implying that the interaction between carbon disulfide and acetone, those intermolecular forces are weaker than the ones between carbon disulfide in itself and acetone in itself. Okay, so this allows more vaporization than it would for the solvent, for example, if it was in its pure form. Okay, I left this in here just, in case you wanted a textbook explanation. Okay, so part C, the solution is not ideal and shows positive deviations from Raoult's law. Therefore, carbon disulfide acetone interactions must be weaker than acetone and carbon disulfide interactions. A solution of benzene and toluene is 25% benzene by mass. Great, another percent by mass question. At 25 degrees Celsius, the vapor pressures of pure benzene and pure toluene are 94.2 torr and 28.4 torr respectively. Assuming ideal behavior, calculates the vapor pressure of each component of the solution, the total pressure above the solution, and the composition of the vapor in mass percent. Okay, so the first two, no big deal. We did this already. The last part, that might be a little bit trickier. but we'll start at the beginning. Okay, so first let's find the vapor pressure of each of the solution components. And I really don't want to run out of room while I'm writing this. So let's just take note of what we know at this point. For benzene, the vapor pressure of pure benzene is 94.2 torr. This is 25% benzene by mass. Okay, so 25% by mass. Okay, so what happens whenever you're given percents? Pretend that you have a 100-gram compound. Okay, so we're going to say we have 25 grams of benzene. For toluene, the pressure of pure toluene, I'm probably mispronouncing that too, shame on me, it's 28.4 torr. And because the benzene is 25% by mass, then the toluene is by necessity 75% by mass. And in our hypothetical 100-gram compound, that means we have 75 grams of it. Okay, so remember that the pressure, partial pressure of the benzene is going to equal the mole fraction of the benzene times that value, the 94.2 torr. Okay, likewise, the pressure of the toluene is going to equal the mole fraction of that substance times the pressure of the pure substance. So a good place to start here is finding the moles of each of these, right? So for moles of benzene, we've been given 25% by mass, but we're saying it's 25 grams. So we got 25 grams of benzene. And let's just convert that to moles. Likewise, for the toluene, we have 75 grams, so we're going to convert that. Okay. Let's find, remember, we only need to find the mole fraction of one of these, and the other one will just be 1 minus that mole fraction. So we'll just, might as well just do, let's do the mole fraction of benzene. Okay, so we're taking the moles of benzene. Actually, I gotta get in the better habit of writing the variables out. I mean, you guys get it, right? Okay, so that would be the moles of benzene divided by the moles of benzene plus the moles of toluene. Just writing in a diagonal for no reason. Okay, so 0.32069 moles of benzene divided by the total moles okay, 0.2822. Okay. Therefore, the mole fraction of the toluene is just 1 minus that, 0.7177. Okay. The pressure of the benzene is the mole fraction times the pressure of the pure benzene. Which was given to us. (26.6 torr). Okay. The pressure of the toluene is the mole fraction of toluene times the pressure of pure toluene. Okay, so then that's 0.7177 times 28.4 torr. And that's going to equal 20.4 torr. Okay, so now we've got the pressures exerted by the individual gases over the solution, the total pressure above the solution. Okay, well, we know that the total pressure is going to be the sum of the individual pressures. Write it down here. 26.6 torr plus 20.4 torr. So 47 torr is the total pressure above the solution. Okay, so you're just adding those together. Okay, so here we come to the last part. We have to find the composition of the vapor in mass percent. Okay, this is mass percent composition of a gas. Keep in mind that according to the ideal gas law, I mean, this is not, we won't be using this formula in this problem, but just as an FYI, remember that pressure is directly proportional to moles. So they change in the exact same way. So like the percentage or the portion of the pressure that's made up by a particular gas will also be reflected in the portion of moles that's made up by that particular gas. Remember from chapter 6 that the law of partial pressures, and this is actually a formula from this chapter too, but this is kind of the way it was written in chapter 6. The partial pressure of a gas is the mole fraction of that gas times the total pressure. Okay, so the mole fraction of that gas, if you wanted to find it, you would be dividing the partial pressure by the total pressure. Okay, so recall in the last question that we were doing, we were talking about the mole fractions of each component in the solution itself, right? Here we're talking about the mass percent or the mole fraction of, yeah, sorry, not mass percent, of the mole fraction of each individual component in the gas phase. So they're not going to be the same as the mole fractions in the solution. So that's an important distinction for this one. So that's why I included this particular law here. Okay, so if we think about this, what if we wanted to find the mole fraction of benzene, right? I'll just rewrite the partial pressures that we found on the previous example. Okay, so the pressure of the benzene was 26.6 torr. The pressure of the toluene was 20.4 torr. And then, of course, the total pressure was 47 torr. Okay, so in order to find the mole fraction of the gas of benzene, we're going to be dividing the partial pressure of benzene by the total pressure. Okay, so that gives us 0.56595 as a mole fraction. Okay, so then the mole fraction of the toluene, we're just going to subtract the mole fraction of benzene from 1. Okay. Now, let's just say that we, like, hypothetically, we had 1 mole of gas total, right? So if we had 1 total mole of gas, and we knew that, for example, in benzene, we knew that for every 1 mole of gas, we had 0.56595 moles of benzene. And then we multiplied that by the molar mass. We would get 44.21 grams of benzene. Likewise, in this 1 mole of gas, if we were to treat the toluene in the same way, okay, so now we've got these individual masses of both of them. Okay, so we're finding mass percent composition, right? So in order to find the mass percent composition of both of these guys, we need to add them together to get the total, right? So I'm just gonna highlight this and move this up here, write it in a different color. Okay, so the total mass is 44.21 plus 39.99 grams, which adds up to about 84.2 grams. So that means that the mass percent of benzene is the individual mass of benzene divided by the total mass times 100. So that works out to be 52.5% benzene. And then to find the percent of toluene, we'll just subtract that from 100. I mean, you don't have to do it this way, but I think it's just a little faster. I mean, in other words, you could just go ahead and calculate the individual percentage for toluene in the same way that I did for benzene, or you could just subtract it from 100. Okay, so benzene, the composition of this gas mixture over the solution is 52.5% benzene by mass and 47.5% toluene by mass. So what does that mean? Which one do you think is more volatile? If you think about it, remember that if you're comparing substances and you're trying to determine which one's going to have a higher vapor pressure, that usually corresponds to the one that vaporizes more easily, right? Because it's more likely to be in the gas phase. So because a greater proportion of this gas mixture is made of benzene, it likely indicates that benzene is the more volatile substance. Okay. Moving on again. Okay, so now we're getting to this concept of freezing point depression. So you know how in the winter the roads are salted, and that's because when salt is mixed with water, the intermolecular forces between the salt and the water cause the water to freeze at a lower temperature than it would normally on its own as a pure substance. So that means that, you know, temperatures can be below freezing and ice will still not form on the roads when they've been salted. Okay. Just, you know, factoid. Okay. Likewise, so there's freezing point depression, and there's also boiling point elevation, where a substance will boil at a higher temperature than the pure solvent by itself. Okay. So freezing point depression is, there's a lot of like 3 variable formulas in this chapter. This is another one of those where it's pretty simple actually. So the change in temperature, meaning like the amount that the temperature changed from the temperature at which something would occur for a pure substance, is the molality of this solution times the freezing point depression constant for the solvent. Okay, so let's just break this down for a second. So temperature in this case is in degrees Celsius. Molality, of course, is in moles of solute per kilograms of solvent. And then the freezing point depression constant is in degrees Celsius per molal. And this is a literature value, meaning like it's something that you would have to look up. It's provided for you in the textbook. Many of these solution examples, the solvent is water. So there's the constant for the freezing point for water, and then there's the constant for the boiling point for water. So when you encounter these questions, look for the word aqueous, because that's indicating that ethylene glycol is dissolved in water. Okay, so again, delta T is the change in the freezing point. It's going to help you find out what the new freezing point is. Okay, so we have ethylene glycol dissolved in water. So it's basically saying like, okay, we know that the freezing point of water is normally 0 degrees Celsius. What's the new freezing point when you add ethylene glycol to it? So according to the book, the freezing point depression constant for water is 1.86 degrees Celsius per molar. We've been given the molality. Okay, so we just need to find delta T, right? This is a plug-in problem. Okay, so delta T is the molality times the freezing point depression constant for the solvent, right? So this is again for the solvent. Okay, so this ends up being, okay, just underline my least significant digit there. Okay, so keep in mind, this is delta T. So we know that since it's freezing point depression, this freezing point is going to be lower than the normal freezing point of water. So you're going to be subtracting this value from 0. Okay, so the freezing point of water is 0 degrees Celsius, and you're just going to subtract. Okay, and This is early significant digit. So this is going to be negative 3.2 degrees Celsius. That's your new freezing point. So just keep in mind when you're finding delta T, you are not finding the final temperature. Remember, like a delta T is, in general, it's the difference between the final and the initial, right? So just make sure that you know that, because, you know, you may not always be dealing with 0 degrees Celsius, right? Okay, calculate the freezing point of a 2.6 molar aqueous sucrose solution. Okay, notice that we don't really need to know anything about the composition of sucrose itself. We just need to know how many moles of it there are per kilogram of solvent. Okay, so again, delta T is the molality times the freezing point depression constant for the solvent. So delta T is going to be 2.6 molal times 1.86 degrees Celsius per molal. And that will be 4.836 degrees Celsius, underlinely significant digit. So the new freezing point is going to be 0 minus that new temperature. Okay, so negative 4.8 degrees Celsius. Okay, so let's just compare these answers for a second. Okay, so just looking back at the previous one, first of all, like, okay, 2.6 molal versus 1.7 molal. So the previous example had a less concentrated solution, and notice the difference in temperature. Okay, so the more concentrated the solution, the lower the freezing point is. Okay. What mass of ethylene glycol in grams must be added to 1 kilogram of water to produce a solution that boils at 105 degrees Celsius? And then the second part, calculate the boiling point of a 3.6 molal aqueous sucrose solution. So the first part, okay, let's just examine this for a second. Has to be added to 1 kilogram of water. So what we're doing here, notice that the new boiling point is 105 degrees Celsius. So the boiling point of water normally, just like the freezing point of water is 0, the boiling point of water is usually 100 degrees Celsius, right? So that means that we raised the temperature by 5 degrees. So that's actually our delta T. It's 1 0 there. Oops. Okay, now the previous problems dealt with freezing point depression. Now we're talking about boiling point elevation. Now instead of having, we're still using molality, but instead of using the constant for freezing, there is also a constant for boiling. Okay, just gonna go back a second. Okay, so this is going to be this value for KB, the boiling point elevation constant for the solvent, which is water, is a different value than the freezing point depression constant. So the constant for water is 0.512 degrees Celsius per molal. Okay. So it's asking what's the mass of the solute that needs to be added to 1 kilogram of water. Okay, so I think the plan of action here is first we need to find the molality of that solution. Then we need to find the moles of ethylene glycol. Then we need to find the grams of ethylene glycol. Okay, that's the strategy. So recall, so I'm going to rearrange this. I'm going to say we need to find molality so that we can get to the moles and then the grams of ethylene glycol. So I'm going to say molality is delta T divided by KB. So in this case, that's 5 degrees Celsius divided by 0.512 degrees Celsius per molal. Sorry, that C looks like an L. Okay. Okay, so this is the molality of our solution. We know that we've got 1 kilogram of water here, right? So let's use that to figure out grams of ethylene glycol. If we have 1 kilogram of water, and now we know our molality, we know that 1 kilogram of water contains 9.765 moles of ethylene glycol, because remember, molality is moles of solute per liters of solvent, or sorry, per kilograms of solvent, excuse me. Then to convert that to grams, we need to use the molar mass of ethylene glycol. The formula has been given here. Okay, so it's about 606 grams, but since we're staying true to our significant figures, okay. So for part 1, we have 6.1 times 10 to the second grams of ethylene glycol in 1 kilogram of water. And that would cause the solution to boil at 105 degrees. Now, calculating the boiling point of a 3.6 molar aqueous sucrose solution, again, that's utilizing this formula. And again, it's aqueous, right? So our solvent is water, meaning that we can use this value again. I'm just going to write it in a different color pen. Okay, so to find delta T, we're going to be multiplying the molality by the constant. Okay, we know that because we're elevating the boiling point, we're going to be adding that to the boiling point of water. Which is normally 100 degrees Celsius. Okay, so there you go. That's the new boiling point after you add sucrose to water. Okay, moving on again to osmotic pressure. So, as you will read in your textbook, osmosis is the flow of solvent from a solution of lower solute concentration to one of higher solute concentration. That's why the chapter opens with talking about seawater and how drinking seawater is very, very bad for you, because seawater is considered a thirsty solution. It wants to accumulate more water, right? It's very concentrated in salt. And so water, because water has a lower salt concentration than salt water does, the water is going to flow into that saltwater concentration. Okay, so as a result, you get severely dehydrated because it's withdrawing all your body fluids, and that's very bad. Okay, so the osmotic pressure is the pressure that's required to stop this flow from lower solute concentration to higher solute concentration from happening. Okay, or to halt it, rather. So osmotic pressure is represented by this capital pi, and that is the molarity of the solution, right? So moles per liter times the ideal gas constant. Remember this guy, 0.08206 liters times atmospheres over moles times Kelvin times the temperature in Kelvin. Okay. So this question, the osmotic pressure of a solution containing 5.87 milligrams of an unknown protein per 10 milliliters of solution is 2.45 torr at 25 degrees Celsius. Find the molar mass of the unknown protein. Okay, well, since it's asking us to find molar mass, we're probably going to need to find moles of this protein. If we have a volume, which we do, been given volume of the solution, and we've been given the mass of the solute, then we can definitely find the molar mass. Okay, so let's just kind of take note of what all of our knowns are. So we've been given osmotic pressure in this question. So osmotic pressure here is 2.45 torr. We've also been given temperature. Remember, temperature for this formula needs to be in Kelvin. And the mass of the solute is 5.87, okay. 5.87 milligrams. I just have a feeling I'm going to need grams later on, so I'm just going to convert that to grams right now. The volume of the solution is 10 milliliters. Again, I have a feeling I'm going to need some liters in here at some point. Okay, so those are all of our knowns. What have we not been given here? We don't know what the molarity is of the solution. That's the one thing that we don't have information for in this formula. So let's figure it out. The molarity is going to be this formula rearranged, right? It's going to be the osmotic pressure divided by the ideal gas constant times the temperature. And I should have done this first. Of course, since we're using the ideal gas constant, we have to convert this to atmospheres. Oops, there's two zeros there. 0.003223 atmospheres. Okay. Okay, so hopefully you can read that. That is 0.0001318 molar. That's the molarity of the solution. Okay, so now we have the molarity, and we have the volume of the solution. And if you recall, molarity is, of course, moles over liters. Therefore, moles is molarity times liters. So we're going to combine these two values. We're going to multiply the molarity times the volume in liters. It's a tiny number, 1.32 times 10 to the negative 6. Okay, now what do we do with this? We need to find the molar mass of the substance, right? Molar mass is in grams per mole, if you recall. So we have the grams of the substance and we have the moles of the substance. So we're just going to divide. And that will give us 4.45 times 10 to the third grams per mole. And that looks like quite a big number, does it not? But we have to remember that we're talking about a protein. So proteins are very large molecules. So the molar mass of a protein would be considerably higher than the molar mass of any of the other compounds we've been doing math with so far in this chapter. Calculate the osmotic pressure in atmospheres of a solution containing 1.5 grams of ethylene glycol in 50 milliliters of solution at 25 degrees Celsius. Okay. Well, this is different from the last problem, but it's using the same variables. And this is actually easier than the last one. Okay, so let's just keep in mind our formula for osmotic pressure. And we've been given 1.5 grams of ethylene glycol. And let's just convert that to moles right now, because we know we're going to need that, right? Okay, the volume of our solution is 50 milliliters. And I'm just going to convert that to liters. Okay, the temperature is 25 degrees Celsius. Let's just convert that to Kelvin right off the bat. Okay, and I think now we have all the information we need. We need to find first the molarity so that we can calculate the osmotic pressure. The molarity, right, is the moles of solute over liters of solution. So we're going to divide the moles of ethylene glycol by the liters of solution. And that'll give us 0.483 molar. Okay, so final step. We're multiplying that molarity times the ideal gas constant times the temperature. .8 atmospheres. Okay, so just remember osmotic pressure is the pressure required to stop the flow from something from a lower solute concentration to a higher one. Think of the semi-permeable membrane. Read about it in the chapter. Okay. So what we haven't discussed yet is something called the Hoff factor. Okay, so this chapter talks about colligative properties, and that's the property of a substance that depends on the number of dissolved particles, not necessarily the kind of particles. Okay, so when we're talking about electrolytes, remember I mentioned electrolytes before. Electrolytes are substances that when they're dissolved in water, they conduct electricity, and ionic compounds are electrolytes, right? Because when they dissolve, they separate into positive and negative ions, charged particles, which are free to move around. And electric current is the movement of electrons, right? So what we have to consider is when an ionic compound dissolves, not only, like, for example, if you're dealing with calcium chloride, right? And it starts out as a solid, and then it separates into its constituent ions. Okay, so whereas before you had one formula unit of calcium chloride, now you have one calcium ion and two chloride ions. Okay, so here you just had one formula unit. Now here you've got three particles. So when we're talking about the Hoff factor, the Hoff factor, which is I, is the moles of particles in solution divided by the moles of formula units dissolved. So if we're talking about calcium chloride, I would be 3, right? Because we've got 3 ions over one formula unit. So our Van Hoff factor is 3. When you're dealing with freezing point depression or boiling point elevation of an ionic substance that's dissolved in water, here for example, or any substance that separates into constituent ions when it's dissolved, this is something you have to take into consideration. Because let's just go back for a sec. Okay, so notice that in our previous examples of freezing point depression and boiling point elevation, ethylene glycol, sucrose, right? Those are molecular compounds that are not ions. They're non-electrolytes. They do not separate into constituent ions when they're dissolved. So we don't have to care about the Van Hoff factor for those because it's always 1, right? Here, the Van Hoff factor can vary depending on what your compound is. So this is just something to keep note of. So we have to update our formula for freezing point depression to accommodate for this value of I. So delta T is now going to be the Van Hoff factor times the molality times the constant. Okay, just like it's going to be the same for the boiling point elevation. Okay. So if we're calculating the freezing point of an aqueous 0.05 molar calcium chloride solution, okay, is negative 0.27 degrees Celsius, what is the Van Hoff factor for calcium chloride at this concentration? How does it compare to the expected value of I? Okay, well, we have the molality. We have the freezing temperature of this aqueous solution. And that's it. And then the constant. This is for water, because remember, water is the solvent. This is an aqueous solution. And now we need to find I. Okay, so let's just rearrange this formula and solve for I. So I is going to be delta T over the molality times the constant. Now, remember, delta T and temperature are not the same thing, right? This is an if. Delta T and like the final temperature are not the same thing. Delta T is indicating the change in temperature. So for us, okay, the final temperature is negative 0.27 degrees Celsius. Sorry, there should have been a decimal point there. And that means that the original freezing point of water is 0 degrees Celsius, right? Pure water, that's the freezing point. So the change in temperature was just 0.27 degrees Celsius. So this should be a positive value. Okay, so the molality is 0.050. And then the constant. So that's going to give us 2.9. Okay, notice that the expected value of I is 3, not 2.9. So you'll see in the book that the more dilute a solution is, the closer the calculated value for I comes to the predicted value of I. Okay, and the reason that I, like the experimental I doesn't necessarily equal the predicted I is because some of these ions will pair back up again. And these formula units will reform. So we don't have as many ions floating around as we would expect to. Now, if you have a more concentrated solution, that's more opportunity for those ions to get back together. So that means that your like actual value of I would probably be much lower than the predicted value. But here, because it's pretty dilute, those charges are separated from each other, it's pretty close to the predicted value. Okay, so for part 2, calculate the freezing point of an aqueous 0.10 molar iron 3 chloride solution using a Van Hoff factor of 3.2. Okay. So, let's see, do I have room to do this? No. All right. Just going to use a pen of a different color. I thought that I incorporated more blank space to make this a little bit more readable for everybody, but I guess I didn't do that. Okay, find the freezing point of an aqueous. Okay, so the molality, this is part 2. So the molality of this aqueous solution is 0.10 molar. Okay, I is 3.2. And we need to calculate the freezing point. So 2-step process. First, we need to find delta T and then subtract that from 0 to get our new freezing point. So remember that delta T is going to be the Van Hoff factor times the molality times the constant for the solvent, which is water. Okay, so that ends up being 0.5952 degrees Celsius. Okay, so your temperature, in order to get that actual temperature, you have to subtract it from 0. Okay, accounting for sig figs, that is the correct value. Okay, so negative 0.6 degrees Celsius. So remember, freezing point depression for an aqueous solution is going to be lower than 0. So it's going to be a negative number. Okay, so just keep that in mind. And then boiling point elevation is going to be higher than 100. Okay. Calculating the vapor pressure of a solution containing an ionic solute. Okay, so we've dealt with vapor pressure with non-electrolyte solutes, vapor pressure with two volatile substances together. Okay, so here we're dealing with vapor pressure and ionic substances. So the challenge here is finding, well, before I get to that, let's just read the question. A solution contains 0.102 moles of calcium nitrate and 0.927 moles of water. Calculate the vapor pressure of the solution at 55 degrees Celsius. And of course, we're given the vapor pressure of pure water at 55 degrees Celsius. Okay, so this is going back to the beginning of this problem set where we're talking about the pressure over a solution and how that's different from the pressure of the pure solvent. So remember Raoult's law. So the pressure of the solution is the mole fraction of the solvent times the pressure of the pure solvent. So this is actually not as hard as it looks. It's just that we have to, based on what we just learned about the Van Hoff factor, we have to accommodate for the fact that an ionic substance, when it dissolves in water, you're going to end up with more moles of ions than you had of the original formula unit. What do I mean by that? Okay, calcium nitrate dissolves into a calcium ion and 2 nitrate ions. So that means that for every 1 mole of formula unit, you get 3 moles of ions. That means that your your predicted Van Hoff factor would be 3, right? But we're just going to keep this in mind because if we've been given 0.102 moles of calcium nitrate, what does that translate to for moles of ions that we have? In order to solve for this vapor pressure, we need the mole fraction of water. The mole fraction of water is the moles of water divided by the moles of everything in this solution. So to find the moles of ions, we started with 0.102 moles of calcium nitrate. And we know that for every 1 mole of that, we get 3 moles of ions. So in total, we have 0.306 moles of ions, right? Now for water, we've been given the moles of water. Great. So the mole fraction of water is going to be the moles of water divided by the total moles. Okay, so 0.927 divided by 0.927 plus 0.306. Okay, so that's your mole fraction. Then to find the pressure of the solution, we have to multiply that mole fraction by the pressure of pure water at that temperature, which is 118.1 torr. And that results in 88.8 torr. So that's a pretty significant drop in pressure. So that says something about the strong, very strong intermolecular forces that are occurring, the ion dipole interactions that are occurring in that solution, right? It's preventing the water from vaporizing as much as it would as a pure substance. A solution contains 0.115 moles of water and an unknown number of moles of sodium chloride. The vapor pressure of the solution at 30 degrees Celsius is 25.7 torr. The vapor pressure of pure water at 30 degrees Celsius is 31.8 torr. Calculate the number of moles of sodium chloride in the solution. Assume the solute completely dissociates. Okay, so like what I was talking about earlier about how some of those ions pair back up again, and that's why the Van Hoff factor might be less than expected. We're just assuming that everything dissociates and doesn't get back together here. Okay, so this is a little bit tricky. Let's think about this for a second. So now we're being asked to find the number of moles of sodium chloride. We have the vapor pressure of the solution, right? I'm just going to write the formula for the vapor pressure of the solution again. Okay. So the pressure of the solution is 25.7 torr. The pressure of pure water at this temperature is 31.8 torr. The moles of water, N means moles, remember, is 0.115 moles. And am I missing anything? I think that's it. Now we're being asked to find, okay, the number of moles of sodium chloride. So if we're talking about the mole fraction of water, remember that mole fraction of water would be the moles of water over the moles of water plus the moles of sodium chloride, right? Now the thing is that we have to consider that sodium chloride, when it dissociates, it becomes two ions. Right? So we go from 1 to 2 here. That means that however many moles of sodium chloride you have, there's actually going to be twice as many moles of ions in this solution. So you have to account for that. Okay? So there should actually be a 2 here. Okay? Because for every 1 mole of sodium chloride, you have 2 moles of ions. So however many moles of sodium chloride you expect to have in this solution, you're going to have twice as many ions. That's contributing to the overall amount of moles that you have, and that affects the mole fraction of water. Okay, so let's figure this out. The mole fraction of water, we can find it another way, right? So right now, we're going to keep this in the back of our minds as to how we're going to solve for moles of sodium chloride. But for now, we have enough information to solve for the mole fraction of water based on the pressure. I'm going to rearrange this. So the mole fraction of water is the pressure of the solution divided by the pressure of the solvent. Okay, so in this case, it's 25.7 torr divided by 31.8 torr. Okay, so now we've got 0.8082. That's the mole fraction for water. This is the same mole fraction as this value. Okay, so why not plug that in, use this information that we have about the actual number of moles of water that we have, and that can help us solve for how much sodium chloride we have. Okay, I'm just going to rewrite that formula down here. So the mole fraction of water, again, is the moles of water divided by the moles of water plus 2 times the moles of NaCl. Because remember, we're not being asked to find the moles of ions. We're being asked to find the moles of NaCl, the formula unit. And there's twice as many ions as there are formula units. So we have to put that 2 there to account for that. Okay. Okay. So the moles of water we have is 0.115. Oh, and I should also say, excuse me, I always put an arrow there. Okay, I should say that. Okay, so now these are our mole, this is our mole fraction for water, right? So 0.8082 actually equals the moles of water, 0.115 divided by 0.115 moles of water plus, I'm just going to call this X because I don't know what it is yet. Okay, so we have to solve for X. So this now becomes an algebra problem, right? So I'm going to multiply both sides by the denominator of this fraction here. So I'm going to end up with, just write it on another line. So 0.8082 times 0.115 moles of H2O plus 2x equals 0.115 moles of H2O. Now you could either distribute this 0.8082 into what's inside the parentheses here, or you could divide both sides by 0.8082. I think I distributed it. Okay, so I'm just going to distribute this value. Okay, so that's going to be 0.9294 moles of water plus 1.616x equals 0.115 moles of water. Of course, I'm running out of room, of course. Okay, bear with me. Okay. I'm gonna write the last part in a different color. Okay. So I'm gonna subtract a 0.9294 from both sides so that I end up with 1.616x equals 0.02206 moles. And then I'm going to divide both sides by 1.616. And therefore, X ends up being 1.4 times 10 to the negative 2 moles of sodium chloride. Okay, so hopefully everybody can see that at the bottom of the screen. And that concludes the problem set for this chapter.